resistor, but not put it in series this time. Put it in parallel. What have we done? Conceptually, what have we done?
Made a parallel circuit.
Pardon?
Made a parallel circuit.
Okay,
They're
Two
parallel
paths
now.
for current.
2 paths for current. So what happens to the current?
Splits.
It increases.
Who said increases?
Increases.
Right. Why does it increase?
Because you decrease the total resistance.
Yes. Okay, to get that concept, this is a much harder concept than this. To get that concept, let's go back to water. If you have water going through a pipe that flows at a certain rate, if you take a second pipe and run it in parallel to that first pipe, how much water you get flowing? More or less? More. You're decreasing the resistance to its flow. Okay. And then, so far non-numeric, we're not doing any numbers here. It's just we have given a second path for the current. So this current is being resisted by R, but now there's another path for the current to be resisted by R. So there's 2 of them. And so you get more flow. Now, this is the equation that's gonna, you won't like, but it's not easy. But when you have multiple resistors in parallel, the resulting resistance, well, what do you think the resulting resistance is just for these two?
If the R's are the same, it's half.
If the R's are the same, yes.
It's half.
Okay. So it's now R over 2. Which, what does that do to the current?
Doubles.
This is another way to write that same equation. Doubles. We're having the resistance doubling the current. Now, what if they're not the same resistor value? Here's the equation you're going to hate. And we'll call this RS for series resistance. RP for parallel resistance is 1, let's put the 1 there, 1 over R1 plus 1 over R2 plus 1 over R3 plus as many as you got. It's not an easy equation with calculators. I'm old enough that first time I did this was without a calculator. But there weren't calculators in those days. But what is this saying? It's saying that, well, let's take our 2 again, because there's a special equation for 2, which is a little easier. If you only have R1 and R2, so that equals 1, I won't even derive it, I'll just show you. It's R1 plus, let's see, I haven't done this in a while, let's see if I get this right. R1 times R2 over R1 plus R2. I may have that upside down.
Yeah, it's upside down.
I have it upside down. The plus is there. And times. So for 2 resistors, it's the sum of the resistors over the product of the resistors. And then, if they're both the same, if they're both R1s, so if R1 equals R2, then it's R1 plus R2 plus R1. So over R1 times R1, which is 2 times R1 over R1 squared. You know, I think I had it right the first time. It's R1 times R2 over R1 plus R2.
I was just thinking of just the denominator, that's all.
So it is R1 squared over 2R1. And there's an R1 that cancels, and you get R1 over 2, half the resistance. This is the special case for two resistors, or two resistances. All right, so this equation, and another way that might be easier to remember it, is 1 over RP equals 1 over R1 plus 1 over R2 plus 1 over R3. This is the same equation as that one, but it might be easier to remember. It's just 1 over everything. So you go in your calculator, you type in R1, you type 1 over plus R2, 1 over plus R3, 1 over, and then equals, and then hit 1 over, and that's your RP, your parallel resistance. All right, so now let's go to another step. What happens if we have more than resistors? What if we have inductors or capacitors? Different or the same?
Different.
The same but different.
It's exactly the same. In other words, you just have to plug in the different kind of resistance. But they behave the same way, they mix the same way.
No, because the series and parallel are opposite.
No, you're thinking of,
You said capacitors.
you're thinking of the value of capacitance and the value of inductance, not the value of the resistance or reactance of them.
Oh, yeah.
Because of that. This is the reactance equation. But let me explain what I just said to you. If you've got resistors in series, this is how you combine them. If you have inductors in series, I'm not talking about combining the reactance now, but just the inductance. Series inductors is just the sum of the inductance. And I didn't say it, inductance is in Henrys, named after Henry, no doubt. And capacitance is in farads. Now, we don't ever see Henrys or farads. We see microfarads. This is where the little numbers come in on this. We see microfarads commonly. Don't even see millifarads very often. You see microfarads, you see nanofarads, and picofarads, especially in radio. You see millihenries commonly, microhenries sometimes. Okay, so where was it? L1 plus L2 plus L3 in henries. Okay, so this is your total henries. Capacitance. Now, here's what you were talking about. When you have, okay, and of course, it's the same thing as resistors with parallel for inductors. Okay. Now, if you have capacitors in parallel, the total capacitance is, now let me draw that for you. Capacitors in parallel looks like this. Here's a capacitor. Here's another capacitor. Here's another capacitor. the total capacitance of these three capacitors is the sum of their capacitance. If they were resistors, what would be the total resistance? And they were all the same. 1/3 of the resistance of any one of them. Okay? If they were inductors, what would be the total inductance of the three? This is similar to resistors. It's 1/3. Okay, so now, capacitors in series, and this is capacitors in series. You have a capacitor, a capacitor, and a capacitor. The total capacitance of the capacitors in series is as if it were resistors in parallel. So capacitors are the opposite, when you combine them, that's the opposite of resistors and inductors. Why is this important? Any guesses why we're talking about all this? Besides just to fill the hour?
It's on the test.
No, it's not on the technician test, but it's important to understand conceptually.
Control the flows?
Yes, controlling the flows, but let's go to the macro level. You're a ham radio operator, you got a radio,
Just in the right
you got an antenna, right? So you have, every antenna has a certain amount of inductance and capacitance built in. It's just part, a feature of that piece of wire at that frequency. Again, the frequency, it affects the way it behaves, the reactance, if you will. Okay, so let's say we talked before about the great big antenna for the very low frequency, and your lot isn't big enough to put that great big antenna on. What can you do?
A coil.
You can put a coil in series, and the coil is an inductance. And you can you can change the frequency of the antenna by adding inductance or capacitance to it. Usually inductance is easier. How much do you change it by? Well, if you put a parallel capacitor, you're adding to the capacitance of the antenna. If you put a series inductor, you're adding to the inductance of the antenna. And then the opposites. You can put a parallel inductor and decrease the inductance of the antenna. You can put a series capacitor and decrease the capacitance of the antenna. So as you get fancier in antenna design, you can use any size lot to work on any frequency by making up for what's not in your piece of wire with components. Okay, you don't know how to do it right now. There's a lot more to it than that, but this is the basic concept. This is how it can be done. You can add or you can increase or decrease the capacitance and inductance in a piece of wire in order to make it work at the frequency you want it to work at. And that commercially is called a tuner. You can buy a tuner, which is, in essence, sits in between your antenna and your radio and has an inductor in it and a capacitor in it. And you adjust the values of those two until your piece of wire, however long it is, matches or acts as if it were the half wavelength at the frequency you want to use. So even with the, what do we say, the 160 meter, pretty much the most used lowest frequency. You don't have 80 meters, which is 240 feet of space to put your antenna on, you can put a shorter piece of wire and make up for it with an inductor and a capacitor. In series and parallel in case you have to increase or decrease. So that's the basic concept. These obviously are used in many more places than antennas, but that's probably the first place you're ever going to see it. When you're trying to put an antenna up at a too low a frequency for the space you've got. I think I mentioned before also the walkie-talkie with the rubber duck. Show us your antenna. Hold up your antenna for us. Okay. You see, I don't know if you can tell, usually underneath the rubber of the rubber duck, there's a coil of wire that is making up for the length that it ought to be. And that's just inductances at work.
So half wavelength is optimal.
Half wavelength is necessary, not just optimal.
So it means like
And so you fake,
down in the base.
but no, even up through here,
Some of them have that too.
probably a coil.
Bob's got one in the middle there.
Now, some of these, also, the one in the middle, is this a two-band? radio?
Tri-band.
Tri-band.
Actually, it's a quad band HT, but it's tri-band.
What it does is, this is not just an antenna lengthening coil, this is a filter that stops the higher frequencies from going up and using this much of the antenna. It only uses this much, because that's all it needs. And then the lower frequencies get through and it uses the whole thing. In the old, no one's probably seen one of these in years, but in the old car radios, the car telephones, remember the little antenna